We're going to talk about logs and exponentials of bases other than e. So logs and exponentials of base, I'm going to call it base b. And we're going to apply calculus to that. So calculus, as in derivatives and integrals. So first of all, let's look at an example. Y equals b to the x. That is a base that could be something other than e. It's not a natural exponential, but by definition, this equals, you can read this backwards or forwards, this means if and only if, we can take the log of both sides, and so this means the log base b of y is equal to x. So there's the relationship there. Now let's look at it a different way. Let's take this and let's take the ln of both sides. So if y equals b to the x, then we can take the natural log of both sides, natural log b to the x. This is a different base, so I can't just throw it away or anything like I could if I had base e. I could just say this is equal to x, but I cannot do that. So according to log properties, this can come down here. So what I end up with is the fact that the ln of y is equal to x times the ln of b. Now ln of y is a variable, x is a variable, ln of b is a constant. So if I want to solve for x, then I could divide both sides by ln b, cancel that, and I get ln y divided by ln b equals x. So I have that information. Now let's try taking the derivative of both sides. So let's take d dx of ln y over ln b is equal to d dx of x, derivative with respect to x. Now ln b is a constant, so that does not require the quotient rule. I'll just pull it out in front. So this is equal to 1 over ln b, that's a constant, times d dx of ln y is equal to the derivative with respect to x of x, that is 1. So just to make this a little neater, I'm going to multiply this over here. So I've got this d dx of ln y is equal to ln b. All right, at this point. Now, what is the derivative of this? Well, the derivative of a natural log is 1 over this amount. So this is 1 over y, but times we've got to take the derivative of y with respect to x because that's not the variable we're looking at. So this is implicit differentiation, is equal to ln b. So then if I multiply both sides by y, I get dy dx is equal to y times ln b. Now what is y? What is it? Well, dy dx is y ln b. Y equals b to the x, so it equals b to the x times the ln of b, dy dx. And what have we just figured out? I know I kind of went all the way around the world here, but what we figured out was that if y is an exponential with a base other than e, then the derivative of y is itself multiplied by the natural log of the base. So we've got a general statement. So general statement, a general truth maybe, okay, that d dx of b to the x is equal to b to the x times ln b. There you go. Okay, so if you've got an example, you don't have to go through all this. You can say find d dx of 2 to the x. Well, it's equal to 2 to the x times ln 2. Pretty simple if you can remember that. Let's try one that's more complicated. Let's take d dx of 5 to the 3x squared plus 9. Well, that is an exponential, so its derivative is itself 3x squared plus 9 multiplied by the derivative of the exponent. We've still got to use the chain rule, but then this was not base e, so we throw this in, ln 5, and it's not really thrown in, it's part of the answer. So anytime you take the derivative of an exponential that is not base e, you have to multiply it by the results, or by the log of the base. Now let's look at a logarithm that is not base e. So let's check out logs. If we've got y is equal to the log base b of x, then that one is not necessarily base e. So that means exactly the same thing as b to the y equals x. Just by definition, if and only if here. So this reads this direction, this reads this direction. Let's find dy dx. So find dy dx. So to do that, we have to take the derivative of this. Well, let me take the derivative of its equivalent instead. So I'm going to do this. D dx of b to the y is equal to d dx of x. Now, a minute ago, we did that already. So we know the process. If it is a base other than e, we just take this and consider it its derivative. Now, we've got a different variable, so we've got to deal with that, and we've got to multiply by ln b. So we've got three things that are going to end up in the answer. We've got the original, we've got times the derivative of the exponent, dy dx, and then we've also got ln of b. Now this side is equal to the derivative of x with respect to x, which is 1. So what is dy dx? Well, divide by b to the y and divide by ln b. So divide by b to the y and ln b. That's going to cancel this and cancel this. So we end up with dy dx equals 1 over, I'm going to write this a little bit differently, 1 over ln b times 1 over b to the y. The 1 over ln b I want to keep. What is b to the y? Well, look here. B to the y equals x, so this is 1 over ln b times x. You might recall that the derivative of a natural log is 1 over x, a natural log of x. So this one, we divide by the log of the base, if it's not base e. So a general truth here. Is that d dx of log base b of x is equal to 1 over x times 1 over ln b. So there's our general truth in terms of derivatives. Now, let's see what happens with with an example. I'll give you an example first. So here's an example. Find dy dx, d dx, dy dx of y equals log base 2 of 4x to the third minus 5x plus 6. Might as well, okay? So here, dy dx equals, well, this is a log, so the original derivative part it's 1 over. Then we've got to take 1 over the ln 2, and then, and you don't have to do it in this order, but I've got to do the chain rule. So the chain rule stuff goes on top. I've got 3 times 4 is 12x squared minus 5. So my final answer has 3 pieces. All right, let's see what happens when we integrate. Might as well integrate these a little bit. So let's take the integral of 2 to the x dx. Now you might recall that the integral of e to the x dx is equal to e to the x plus c. So this one, almost the same. However, we've got a base. So what happens is things reverse when you're integrating. This is 2 to the x, but since we reverse things when we integrate, we've got to divide by ln2 and then put plus c. So why does that happen? Well, let me let u equal 2 to the x, all right? So if we want to do that, then what is dx? Well, du dx is equal to the derivative of this. I'm just doing substitution. Du dx is 2 to the x times ln 2, all right? So substitution, we tend to take this and set it over here. So what we're trying to do is we are trying to rewrite this in terms of u. Well, it's almost all just du, except it's got this extra ln2. So here's the deal. Du over ln2 equals 2 to the x times dx. So I replace this. I've got du, 1 over ln2, kind of cram it in here, du, so this is 1 over ln2. Well, if this is du, then it becomes u plus c. What is u? U is 2 to the x plus c. So there's where my process comes from. So it appears that I am just dividing by ln2, but there is reason for that. Let's check out what happens in general then. So a general truth here is that the integral of a base b, let me just say to the x, this is not the most complicated one on the planet, but this is equal to b to the x over ln b plus c. That's a general fact, and we can prove that if we want to, the same way we did this. Now let's see what happens with a logarithm integration that has to do with logs. All right, so what would you do there? Well, you know, you usually have answers that are logarithms. So if I happen to have something, you know, this one's not quite as cut and dried as the other ones, but if I have something like this, say I've got 1 over 9x squared plus 8x, okay? Now I'm going to make this look really obvious. So I'm going to take 18x plus 8, so I'm going to put 18x plus 8, and then let's say here I've got the ln of 3, all right? So dx. Well, if we pull out the ln 3, we could say this is 1 over ln 3, because that's a constant, and then we've got this 18x plus 8 over 9x squared plus 8x dx. Pretty obvious maybe that the derivative of this is up here. So if you let u equal 9x squared plus 8x, then du equals 18x plus 8 dx. So we've got du over u, so we've got 1 over ln 3, and then we've got the integral of du over u, which is, this is the natural log, so we've got 1 over ln 3, and then natural log of u plus c. And so I'm actually dividing by that, And you could work this out a little bit if you want to, a little differently. This is just a constant, but you've got natural log of u over ln 3. Now, that does not fit log properties. So there you go. What is natural log of u divided by ln 3? That might be something that's interesting. You may have seen a log base changing formula somewhere. Okay, so let's see if we can kind of figure out what that is. Now, just for ease of use, I'm going to take the absolute values off for a minute, but I'm going to call that y. I'm going to say y equals ln u over ln 3. Okay, so just to make that look a little simpler, I'm not really trying to fudge on that. So if I move this over here, I've got ln 3 times y equals ln u. Now, what is u? You know, maybe we want to solve for u. Well, we know what u is. It's this. I haven't really written the answer very well. I guess I should have gone up here and written the answer, right? It was 1 over ln 3 times the ln of 9x squared plus 8x plus c. Get that so you can see it. Whoops, there you go. Okay, I kind of went off on a rabbit trail. Sorry about that. I didn't finish my answer. There's the actual answer. So here, what is this? Let's just take a look at this. If I want to figure out, you know, how u and y are related, then I might want to undo the ln's just for a moment. So to undo the ln's, I need to take e to both sides. So e raised to the ln 3 multiplied by y is equal to e to the ln u, which is u. This one is u. By definition, log properties and that sort of thing, okay? So this is u. Now, what else do we have? Well, if we took this and talked about this, it's ln 3 times y. So this is e to the y and then actually times ln 3. Well, to multiply exponents, you have to raise to a power like this. Okay? So it's actually like that. It's e to the y raised to the ln 3. Well, let me swap these out. That's equal to e to the ln 3 and then raised to the y. And I know that looks kind of strange, but multiplication is something that you can do commutative property on, so it doesn't matter what order you're doing it in. And so now e to the ln 3 equals 3. So this is 3 to the y. So we actually have u is 3 to the y, so that's a base change, okay? So e to the y. Now, if we went back up here and did that with this, we'd have some results because we had ln u over ln 3. So that's our y value, all right? And so we've got 3 to the y. Well, this whole thing, okay, so we had y is equal to ln of 9x squared plus 8x over ln 3. I'll take the plus c and put it on later. So what do we have here? Well, this means that it's 3 to the y, okay? So that our u value, we had, I think I named this incorrectly, didn't I? Nope, I had y, okay? So this is y, so that means that 3 to the y is equal to what we were dealing with in terms of u, so it's 9x squared plus 8x. So 3 to the y, so 3 raised up to the ln 9x squared plus 8x over ln 3. So ln 9x squared plus 8x over ln 3 is equal to 9x squared plus 8x. And maybe pretty obvious on that score, but anyway, you can kind of see that. And so we actually have some values that we could talk about in a different way. Now, you might not want to do that, that's fine, but when you divide by ln 3, then that was related to the base change. So just playing with a whole bunch of algebra, this is a perfectly fine answer. And the only thing that would have caused us any reason to do all this would have been if we would have had it multiplied or something like that. So anyway, just playing around with that. But the integral of something could have a base change in it. And so notice that the answers could actually look different. I could have done base 3 instead. So if I wanted to, because of all this relationship, I could have said, this is equal to the log base 3 of 9x squared plus 8x plus c. And then my answer would have been a little different looking, but it would have been equivalent. So using all this, which kind of almost seems a little bit wild, we can go up to there. Now, do you have to do that? Most of the time, no. But just a little bit of evidence about that. So base changing formulas in integrals, logarithms in integrals, not quite as common. Log base changing formulas with integrals of exponentials, a little bit more common. So there you go.